Hi, I'm Xuejun from Carleton University. Today I will introduce my paper, Partial Label Learning by Entropy Minimization. First, let's get to know what is partial label learning. Partial label learning is regarded as a weakly supervised learning framework. It's also named as ambiguous label learning or superset label learning. Partial label learning deals with a problem where each training example is associated with a set of candidate labels, but only one of which is assumed to be valid. Actually, due to the difficulty in collecting the clean label data, partial label learning has been widely applied to many real-world scenarios, such as web mining, automatic image annotation, ecoinformatics. Inspired by the entropy minimization strategy, which is widely used in the semi-supervised learning, forcing the confident prediction of the unlabeled data. In this paper, we follow the same idea to try to make confident predictions of the partial labeled training data. And the experiments on a number of datasets demonstrate the effectiveness of our method. So let's take a look at the notations first. We denote the partial label training data by D, where small xi is the data instance, and si is the set of candidate labels. M is the total number of training examples. The capital X is the training data matrix, and the capital Y is the partial label matrix. N is the dimension of data, and L is the total number of classes. Here we use a probabilistic classifier F, and we design the objective function as this equation. L is the loss function, H is the entropy function, and omega is the regularizer. And we also put a constraint on F to make Fx is smaller than or equal to yi plus epsilon. Yi is a one-hot label vector, and epsilon is a vector of small scalars. Then by incorporating the constraint as a hinge loss into the objective function, we get the final optimization problem as this equation. The first term is the loss function. Here we use the mean squared error loss. The second term is the entropy function, which is minus f times log f. And the third term is the hinge loss, which is our constraint. And the last term is the regularizer to control the complexity of model. Here we use the L2 norm. It's worth to notice that the entropy term encourages the model to make confident predictions for the training data, so that the ground truth labels are likely to contribute more to the model training. And also the hinge loss term enhances this target. This optimization problem can be solved by stochastic gradient descent. So the last part is the experiments. We test our model on 5 real-world partial label datasets. For our model, we use a 3-layer neural network as a classifier and apply softmax function to the final layer to get the probabilistic outputs. The first table shows us the characteristics of datasets, which are birth song, lost FG night, soccer player, and Yahoo News. And this table also gives us the total number of training data, the dimension of features, the number of classes, and the average of candidate labels. The second table shows the mean classification accuracies of our model and compared methods. We deploy pairwise t-test at 0.05 significance level to investigate whether our model significantly outperforms the compared methods. The circle bullet symbol means our method statistically outperforms the compared methods, and the empty bullet symbol means otherwise. The results without any symbols means our method is comparable to the compared methods. So from this table, we can see our method significantly outperforms, or at least is comparable to most compared methods in most datasets, which demonstrate the effectiveness of our methods. So that's it for my paper. For the future research direction, we are considering if we have a bunch of unlabeled data, how to make use of the information of unlabeled data to help partial label learning would be an interesting direction, which is to combine semi-supervised learning and partial label learning together. So that's it. Thanks for listening. Thanks.